Welcome to Einstein Mechanics. In this episode, we are also going to continue the studies on capacitors. Here, we are looking at energy stored in a charged capacitor. So, we have the idea that capacitors store charges. And here we are to investigate the energy stored when it is charged, the strength, the work it can undergo when it is fully or partially charged. Are we okay? So now we have to understand that a capacitor stores charges in the form of electric field. So first, we have to know that a capacitor stores charges in the form of an electric field. Are we okay? And we also have to know that the amount of energy stored is directly proportional to the capacitance. So the amount of energy, the energy we want to find, the stored energy is proportional. The amount of energy stored is proportional to its capacitance. So the larger the capacitance, the larger the energy stored. The lower the capacitance, the lower the energy stored. Now, we are going to let the letter W be the energy stored. So, someone may say we could have used E to represent the energy, but here, throughout the episode, we are going to use W as the energy stored in a charged capacitor. And the formula for the energy stored in a charged capacitor, W, is going to be half the capacitance and the voltage square. So once we know the capacitance of the capacitor and the applied voltage to its terminals, we are able to calculate the energy stored. So this is going to be our equation 1. And we have to take it into consideration that the unit for energy is what? Joules. Are we okay? So the energy stored in a capacitor is going to be measured in joules. This equation, we can still modify the equation from this expression. C is equal to Q on V. And we also have Q is equal to CV. We have V to be equal to Q on C. So if we are to bring into the equation 1, we are going to have a modification as the energy stored to be half kV. Are we okay? So this is what we are also going to have. If we are bringing in the C as K on V, we are going to have this equation as our second equation. And if we are bringing in the expression for V, then our W, which is the energy, is going to be half Q square on the voltage, or Q square on the C, which is the capacitance. Are you okay? So this is going to be our third equation. So any of these equations can help you find this energy stored in a charged capacitor, which is very simple, and it is in joules. We are going to write J. Are we okay? So straight away, let's solve some simple examples on this and look at how it is going to be. A 250 microfarad capacitor is to have energy content of 125 joules in order to operate a flash lamp. Now, what voltage is required to charge the capacitor? And the B part says how much charge passes through the flash lamp. So straight away, let's look at the content of the parameters. Now we have our C, which is the capacitance of the capacitor to be 250 microfarad. Are we okay? Now we also have the energy content. The entire capacitor is able to store energy as 125 joules, and we are to find the voltage V, which is being applied to the terminals of the capacitor. Now, from the equations we wrote, we have W to be equal to half CV squared. Because we have the capacitance, we have the energy, we can find the voltage. So this is going to help us. If we have V, that is going to be square root of 2 the energy on the capacitance, and this is going to be equal to, now, square root of 2 times the energy, 125, and the capacitance is 250 to the power negative 6. This is going to give us voltage of what? 1000 volts. Are you okay? So we need a voltage source of 1000 volts to charge this 250 microfarad capacitor to an energy level of 125 joules. Now the B part, how much charge passes through the flash lamp? So we are interested in the charge, and from the equation C is equal to Q on V, we can calculate the charge, which is Q on CV. We know the total capacitance, which is 250 to the power negative 6, and the required voltage, which is 1000 volts. So this is going to give us a charge of 0.25 coulomb. Are we okay? So this flash lamp requires a charge of 0.25 to operate. Let's look at the second example. So pay attention here. A capacitor is made with 10 plates connected. So we have 10 plates capacitor and separated by sheets of mica or mica with relative permittivity of 6 and having thickness of 0.2 millimeters. If the capacitance of the capacitor is 23.9 nanofarad and the applied voltage is 500 volts. Now determine the area of the plate, the charge stored, and the energy stored. So straight away, let's find our parameters. We have number of plates to be equal to what? 10. And we have the relative permittivity of the mica to be what? 6. We also have the thickness of the dielectric to be 0.2 millimeters, and that is going to give us 2 to the power negative 4 meters. We also have the capacitance of the capacitor to be 23.9. Now, the prefix nano is 10 to the power negative 9 farad. Are we okay? And our voltage is also giving us 500. So very simple, we can calculate the area. We know that for capacitor with n number of plates, we are going to have our capacitance C to be equal to, we have this is our formula, and now we are interested in finding the area. So meaning the area is going to be our capacitance multiplying that, everything on that. Are we okay? So here, let's take the permittivity of free space to 8.85 to the power negative 12. And our area is going to be, now the capacitance, which is 23.9 to the power negative 9. The distance between the plates is 2 to the power negative 4. Now, we have 8.85 to the power negative 12 multiplying 6 and 10 minus 1. When you punch this on your calculator, your area is going to be 0.01 meter square. Are we okay? So this is the area of the plate. Now let's look at the charge stored. The charge stored, which is the II. Now from C equal Q on V, we are going to get our charge stored to be C on V. This implies that our Q, the charge, is the capacitance of the capacitor, which is 23.9 to the power -9, and the voltage is 500 volts. So we have 500 volts. So this is going to give us a charge of 11.95 to the power -6, that's, or 11.95 microcoulomb. The third part says we should find the energy stored, and we know that the energy stored in a capacitor is half CV squared. We have our half, the capacitance, which is 23.9 to the power -9, and our voltage 500 squared. So everything here is going to give us 2.9875 to the power -3 joules. So this is the energy stored. Thank you for watching this episode on energy stored in a charged capacitor. See you in the next episode. Kindly subscribe, share, and drop your comments. Thank you.